Okay, so we should start. The next presentation is engineering critical assessment of an antenna tower steel shell elements welded joints, presented by me. Okay, so as an overview of the presentation, so in the first will be an introduction of the matter and the problem in the civil engineering constructions. The second approach of engineering critical assessment on a real case assessment. We will see an antenna monopole type structure, and in the end the conclusions. In the mechanical engineer approach, we do have the fracture mechanic approach. We do have the stress and the defect. We could have the stress and the defect, and then the design. In the end, the manufacture, and of course, a service life prediction or inspection intervals prediction as well. In the civil engineer structures, loaded in low cycle fatigue or high cycle fatigue. We do have the stress, we do have the design also in the next phase. In the next phase, design, of course, it's done with the provision, Eurocode in Europe provisions, and anyway, we can we have a requirement regarding the service lifetime. And in the end, we do have a manufacture and the erection of the structure. Together with the provision of EN 10090, we have also the execution and the quality control. Again, we have the inspection intervals precisely indicated by the EN 2000 and other provisions from the Eurocode. But at the inspection, we do have a defect. In that phase, we need to repair the structure. We have a problem in this point, because we need to repair, and of course repairing means maybe for a steel structure, that is for a steel bridge, we need to close the circulation, the traffic, and so on. So it's a probability of money anyway. So it's needed another approach for the low cycle and of course the high cycle fatigue structures, especially in this case shell type ones, to assess from the beginning the presence of the flow. When we do have a flow, of course in the structure we can have failure in the lack of failure of an subassembly, and in the end, if the structure suffers for a lack of redundancy, we can have a collapse. That's maybe an example here, a windmill tower. Following the post-factum assessment, the results were that principal damage causes were the defects, especially the weld defects and of course the corrosion types. As I said, there is a need for a new approach, a better safety of the structures, applying a method for structural integrity assessment. As an answer can be the engineering critical assessment, which can be done due to assess the implication of a possible flow discovered in a structure, or to assist in the choice of the welding procedure, or to assist in the inspection techniques. Establishing the remaining lifetime of a structure or an element of a structure under cyclic loading, of course we all know it's supposed to apply a damage accumulation principle. As the phases, we do need to know the load range. That's maybe a problem we'll see afterwards. Determining the fracture material properties, of course fitting the element with the flow in a one preset flow types. Defining the initial flow dimension, another problem. Defining the crack growth limit, we will see what we can apply. We can apply a British standard here, and applying the crack-grow power law, the Paris law, and in the end determining the number of cycles from the initial crack to grow to the critical crack size. In this way, of course, it can be calculated the number of days, years under service, the structure until the failure of the element. Of course, the assessment can be done if there are known the resultant stress, the material fracture toughness, the geometry, and the crack size. The purpose of the research is to apply fracture mechanics in the assessment of the steel shell structures, elements, from the designing phase, as I said before, and to determine if possible mat flow in the lifetime of the structure can be dangerous to the service of the structure, and of course if it will be needed the repair or not. In this way, it was done, this type of approach in a real case assessment. It was assessed, the engineering critical assessment was done for a real case, an antenna tower, a monopole type, you will see immediately. The need was that the investor wanted to find the reliability of the structure, because there are 15 antenna towers that will be mounted. So it was needed to know the reliability in time. So it was needed to apply the ACA from the beginning of in the designing phase, from the beginning of the designing, more or less. From the geometry point of view, it's a monopole antenna type 30 meter high with 3 segments, 12 meter, 2 of 12 meter and 1 of 6 meter. The diameter is it's 610 millimeters. It's a circular hollow section type, a profile 1. And at the top we do have a service platform, which is around 4 meters from the top. This platform, of course, it is a problem because the wind loads were increased, and of course the reactions at the base were higher. And we will see immediately the wind assessment. Regarding the fracture mechanics point of view, we did use K1C from the SynTAP procedure, establishing the correlation between the Sharpie test results and K1C. So we use this because of the quality of the steel. The quality of, we'll see, it's S355. It's a commonly used steel. That for this steel it can be used, this procedure. It's okay. And of course the investor provided also the parameters regarding the Paris law parameters C and M. Regarding the flows, in this table I shown some dimension regarding the initial flow length and the types of the flow. It was taken into account 10 types of flows from the through thickness flow type and the edge flow type. Each flow type is described as a position in the structure, in the element. We will see immediately, because we do have a portion of the structures as the analysis results. And of course, it was needed to design this structure. And after the design phase, we wanted to have in more depth analysis. It was needed a finite element method for assessing the stresses nearby the joints, especially of course the joint on the foundation and the joint segment joint, the first segment joint. It was applied, of course, the wind loads from the Eurocode with a recurrency interval of 50 years. We'll see immediately. So it was used 2 models. One, as I said before, for the connection at the base, and one of the first segment to the second one. I will not get into details here. It was done with the Baco software. Used some boundary condition for the forces that came from the analysis, for the bending moments, of course, axial force, shear force. In the end were determined the stresses in the areas of the possible mat flows. We'll see immediately. But here is a discussion regarding the value of the flows. Why? Because we didn't take the values of the peak stresses. As we can see, 510 megapascals is over limit. That means that the element in the area of the possible flow, let's say, it will enter in it will overstep the limit of the steel. So we will not use these. We will use the average. The average, which has been calculated on the let's say crack path intuition. So crack intuition path. It's not so good explication. This crack intuitive path. But it was used not the maximum value, just the average one. So as you can see, we assessed in each possible, let's say, area of flows, welding between the stiffeners and the wall of the tube, and of course also it's the nearby the bolts connection. This is for the first model, and for the second one, again, the stiffeners and the bolts type. Each flow was assessed, and for each flow was calculated an average value of the stress. Of course, this was done for 50 years recurrency of the wind load. It was needed to evaluate the cycling loading of the wind load, because we do not have a peak value of the wind speed. So we needed to have distribution, we will see immediately, of the wind load. So for that reason, it was taken into account some measurements from the National Institute of Meteorology and Hydrology, from Romanian Institute, and it was giving in the end the measurements for the time of 1 year. These measurements were arranged in the following probability density function using Weibull distribution. So in the I will not enter into details. In the as an input, we did have 5 analyses redone for this is the maximum average of 50 years. So it were done another 5 analyses for assessing the wind load and of course the stresses in the end for each type of flow area. It was arranged. Of course, it was needed to have the stress ranges and an annual frequency. So we passed from the wind speed to the stress frequency, let's say more or less. So here we can see a table just for one type of stress. It was done the frequency annually and monthly, of course, and the number of cycles, the number of total cycles for 1 year. So we can see, for example, the 260 megapascal, it's around 0.0025 monthly frequency. In the end, of course, we would like to apply these loads for the fatigue loading. For that, we did calculate it. But having the fatigue load, we need to have also the critical size of the cracks. So we did apply the British standard 7,910 failure assessment diagrams level 2, and for each type of flow, it was determined the critical size of the flow. Some information about the input data, and in the end, of course, we needed to apply the fatigue base on ACA using the cycling loading as presented before in the number of blocks. Each block represents 1 tier. It was used also the one slope Paris law type, so it was done, of course, a simpler procedure from the British standard. In the end, calculating the number of the cycles needed for a crack to extend from the initial crack size to the critical one. So in the end, we we have had the number of blocks. So this is the number of years, equally to 7,327 cycles. And we did, in the end, find out when the flow will reach, the crack size will reach to the dimension, the critical dimension. Okay, it was presented also the remaining life in this way. Sorry for passing because I overlimited the time. So I will close the presentation right now. I'll finish the presentation. So in the end, it was done some comparative graphs between the types of the flow, so we can see the through thickness flow, and from reaching the number of the crack size in the final stage, the critical crack size, and the number of years, the numbers of blocks. So in this way, we can predict the lifetime of a structure from the designing phase, which in this way it's a good thing, because we, civil engineering, we are not proceed like this. We are thinking of the design itself just to last, for example, 50 years and so on. And that's all. As a conclusion, the proposal, as I said, is to apply ACA from the designing phase, and I will underline some downsizes. The crack closure effect is neglected, of course. It's a simple one. This is maybe one of the major problems. The initial crack size, it was applied the Haddad's criterion. Obtaining K1C, it will be difficult to obtain K1C if it will be used high strength steels. If you do use 235 or 355, it's okay. But if you go up, you do have a problem applying Bannister syntax procedure. So, and another downside, it will be that obtaining the loads and the stress values are implying a very much amount of work. So it will be needed to have a very hard work in this matter. So thank you for your attention, and excuse me for over limit. So the next presentation.